So, good morning, dear students. Today we'll start discussing about the conductometric estimations. So, in the conductometric estimations, which you have done it in the lab, it is similar to the what you have done in the first instrumentation. That is potentiometric estimation of an phase. Here in the first experiment which you have done, the potentiometric estimation where redox reactions are carried out. And the platinum and calomel electrodes are used, and the conductometric estimations is quite similar to the potentiometric estimations, but only thing is that this is an acid based neutralization reactions. So uh, when you look into the Ohm's law, now when a current I in amperes flowing in a conductometer is directly proportional to the applied EMF, that is volt, and inversely proportional to the resistance in ohm. So I is equal to E by R. So the reciprocal of this resistance is that is 1 by R is called as conductance, and is expressed in Siemens per meter or mhos. The theory involved in this conductometric titration is the electrolytic solution depends on the nature, number, and the mobility of the ions in the solutions. So, conductometric conductivity of the ions depends upon nature of the ions. So, nature in the sense the oxidation states of the ions, the +1, +2, +3, so on. Number is the quantity of the ions, 100, 200, 300 ppm likewise, and the mobility of the ions, so how faster these ions can move in the solution. So these are the three important factors by which the conductance of any aqueous solution depends. Now, larger these ionic concentrations and smaller the ions can migrate to the electrodes in a faster rate, hence you get more conductivity. So larger concentration of these ions and the faster moving of these ions, how fast these ions can move in the solution. So that will give you the more conductivity of the solution. So that is the principle of a conductometer. In the instrumentation, when you look into the instrumentation part is concerned, it consists of two platinum electrodes. So the two platinum electrodes having a cross-sectional area of 1 centimeter square, and they are kept at a distance of 1 centimeter apart. And when you dip these platinum electrodes into a solution and measure the conductance, the obtained conductance is called as a specific conductance. And the platinum electrodes having a unit area of cross section, that is 1 centimeter square, and they are separated by at a distance of 1 centimeter and kept in 1 molar of the solution. Molecular weight of the solute dissolved in the solvent, 1 molar of the solution. That conductivity or conductance is called as a molar conductance. So here you are going to measure the specific conductance, and this is the instrumentation where you can see very clearly the beaker. In the beaker, a mixture of an acid, mixtures of two acids, one is a strong acid and one is a weak acid is taken, and stirrer is kept for the water to circulate in between the platinum two electrodes, and these two electrodes having a cross sectional area of 1 centimeter square, and they are kept at a distance of 1 centimeter, and these two platinum electrodes are connected to the conductometer. And for the titration, it's a simple acid based titration. NaOH is added from the burette in 0.5 cc wise. When you add sodium hydroxide in the 0.5 cc from the burette to a known volume of an acid mixture, let us consider an acid mixture of the type HCl and acetic acid in different proportions are mixed with each other. Now HCl is a strong acid, acetic acid is a weak acid. A strong acid mixture of a strong acid, strong and weak acid, both are mixed with each other, acid mixture. and it is titrated with a strong sodium hydroxide solution whose normality is known. Now during the reaction, what you have to do is you have to pipette out a 50 ml of an acid mixture into a solution, acid mixture solution into a clean 100 ml beaker. Either you can, any volume you can choose, 50, 100, 200 likewise. Now conductivity cell, that is the platinum electrode, is dipped into the solution, and sodium hydroxide is added from the burette in 0.5 increments, and the specific conductance of the solution is noted. Now how does this conductivity changes in the solution? Now after the you get a significant increase in the conductance. Your conductance goes on decreasing initially, and there is a incremental increase after a certain period of time of addition of 0.5 ml of sodium hydroxide from the burette, and the conductance significantly increases. It goes on increases, and it becomes an increased value and stays at that value after certain addition of sodium hydroxide. So after that you have to take 6 readings and plot a graph of specific conductance versus volume of sodium hydroxide, and from this graph the neutralization points of strong acid as well as weak acid both are calculated. Neutralization points of strong acid, let us consider a V1 ml, and neutralization points of weak acid. Weak acid dissociates over a period of range, so we have to calculate V2 minus V1. How does this conductivity of acid mixture, especially when strong and weak acids are taken? In the strong acid is one which completely dissociates in the aqueous solution and exists as ions, and weak acid is one which partially dissociates in aqueous solution and exists as ions. Now observation and calculation. The serial number 1, 2, 3, volume of NaOH, you are adding 0.5, 1.5, so on. You have to measure the specific conductance, and calculation is very simple here. N1 V1 of the acid mixture is equal to N2 V2. Now from this you want individually, so N of normality of HCl is equal to normality of NaOH into V1 that you are obtaining from the graph, that we will see when we are explaining in the applications. V1 from the graph NaOH, and divided by V mix. V mix is the initial amount of acid mixture which you are pipetting out. Now N of acetic acid is equal to normality of the acetic acid. Again same, normality of NaOH into V2 minus V1. This difference you have to calculate because acetic acid is a weak acid. It will dissociate over a range, and divided by V mix. Now amount of HCl, normality into 36.5. 36.5 is the molecular weight of HCl. Hydrogen is 1 and fluorine 35.5. In total it is 36.5. So normality of HCl into 36 point, if you multiply, you will get so much of amount of HCl in gram per liter. And normality of acetic acid is calculated, and that is multiplied with the 60. 60 is the molecular weight of acetic acid. So the you will get so much of gram per liter. So when you conductometrically estimate, you can calculate the normality of both strong and weak acid, and amount of both strong and weak acid. Now when you look into the applications, so in these applications you have to study 3 different aspects of this conductometric titrations. The first application is applications of a strong acid versus strong base. Now you know very well, strong acid is an HCl, strong base is an NaOH. So it's a simple neutralization reaction. HCl reacts with NaOH, and it will give you salt and water, sodium chloride plus water. Now this titration, when you do it using conductometer, initially the graph, when you record the specific inductance and volume of NaOH and plot the graph, you get like these two straight lines. So these the first straight line corresponds to the continuous decrease of the strong acid by a strong base, and this is due to the replacement of H plus from HCl by an OH minus from the base. So HCl is a strong acid which dissociates completely and exists as an H plus in the solution, and it will be immediately consumed by the OH minus strong base. So the H plus is the smaller ions, and it will give rise to more specific conductance. And when it will be replaced by sodium hydroxide, H plus goes on decreasing in a solution, and you get decrease in the specific conductivity. In this case, this first straight line is corresponds to the consumption of H plus from HCl. Now, after the consumption of H plus from HCl, what you have to do is, after getting the end point, further you are going to add sodium hydroxide. That is what I said in the previous sentence. After the consistence increase, you have to get, after the consistence decrease, you have to get a significant increase. So you are further adding sodium hydroxide from the billet to the solution. So sodium hydroxide contains OH minus ions, and these OH minus ions will contribute in the conductivity. And after the end point, further if you add, you will get a significant increase in the conductivity. So you can see second straight line is corresponds to a significant increase in the conductivity. This is due to the excess of OH minus ions which you are adding even after the neutralization. So you get two straight lines in the first case. The first continuous decrease is due to the consumption of H plus from HCl, and a significant increase is due to the presence of excess of OH minus, and intersect these two straight lines, and from the intersection point extend the line to the x-axis to get the volume of NaOH to required to completely neutralize the HCl. And the calculation is very simple. N1 V1 of HCl is equal to N2 V2 of NaOH. Now N1 is normality of HCl you need to calculate, and the volume of HCl V1 you can which is known when you are pipetting out 50 cc, 25 cc, so on. Normality of NaOH will be known, usually 0.5, 0.25 or even one normal NaOH will be taken, and volume you can obtain from the graph. So normality of HCl is equal to a normality of NaOH into a volume of NaOH from the graph divided by volume of HCl which you are putting out, and from this normality you multiply with 36.5, you will get so much of gram per liter. So this is the first case of applications, that is the reaction between a strong acid versus a strong base. Now in case of the second application, it is the reaction between a weak acid versus a strong base. Now let us consider the weak acid of acetic acid. Acetic acid reacts with acetic acid. Weak acid is one which dissociate partially in aqueous solution. So acetic acid dissociate partially and exist as acetate minus plus HCl H plus. Now the dissociation percentage will be less. It will not completely dissociated, like 20% or 20% will be dissociated, and the rest one will remain as undissociated molecule. Now when you look into this reaction, CH3COH plus NaOH gives rise to CH3CONa plus H2. It will form a sodium acetate. Now when you start adding sodium hydroxide to a beaker containing acetic acid, weak acid, conductance, specific conductance, it will increase very slowly, This slow increase is due to the slow dissociation of acetic acid or partial dissociation of acetic acid and exist as H plus and acetate minus. So conductance values incremental increase. You can see the first straight line is corresponds to it. It is slowly it is increasing. It is not a steep increase or a significant increase. It is a incremental increase. A very incremental increase of acetic acid dissociation takes place in the solution, and hence you get the incremental increase of specific conductance. And after the neutralization, further if you are going to add sodium hydroxide, and that sodium hydroxide contains highly mobile OH minus ions, which significantly contributes to the conductance of the solution. When all of the H plus from acetic acid will be consumed, now you get another straight line which in which you can see specific conductance value considerably increases. Now intersection of these two straight lines will give you a point. That point, when you extend it to the x-axis, you get the volume of NaOH. So in this application, that is application of a weak acid versus a strong base, initially conductance value increases incrementally, and after the neutralization, further addition of sodium hydroxide increases the conductivity considerably. The intersection of the two straight lines will give you the point, and that point, when you extend that to the x-axis, you get volume of NaOH. So the calculation to calculate the amount of acetic acid in this case, N1V1 of acetic acid is equal to N2V2 of NaOH. Normality of sodium hydroxide will be known. Volume of sodium hydroxide required you can calculate from the graph, and normality of acetic acid is pipetted out. Volume of acetic acid pipetted out is known. Normality of acetic acid is calculated like N of acetic acid is equal to N of NaOH into V of NaOH divided by V of acetic acid. So you can easily calculate normality of acetic acid is equal to normality of NaOH into volume of NaOH, which you are obtaining from the graph, and divided by volume of acetic acid which you are putting out, divided by V. In the third case, which is a mixture of a strong and weak acid versus a strong base, this you are doing in the practical. In this case, as I said, as long as the HCl is present in the solution when it is mixed with the acetic acid, as when HCl is present in the solution, the HCl first undergoes ionization, because strong acid will always suppress the dissociation of the weak acid. That is what is the phenomena is called as a suppression of dissociation. So as long as this HCl is present in the solution, it will not allow acetic acid to undergo ionization or dissociation. So when you look into the reaction, HCl plus acetic acid, when you titrate with the standard solution of sodium hydroxide, that is 0.5 cc from the burette, you will get sodium chloride plus sodium acetate plus water. Now during this titration, when you look into the changes in the specific conductance versus the volume of NaOH, you will get three straight lines here, because in the first case the continuous decrease in the specific conductance will be observed. Now the specific conductance continuously decreases, and this decrease in the specific conductance is due to the replacement of H plus from HCl by OH minus from the base. So the HCl is a strong acid which completely exists as ions, and that ions, the one which is the ion which is the smallest in size, will give you largest specific conductance, that is H plus, which will be replaced by continuously by sodium hydroxide. Now continuously when you add sodium hydroxide, H plus of HCl will continuously consumed, and hence the specific conductance continuously decreases in the first case. So you can see the specific conductance value continuously decreases. There is a very decrease in the specific conductance. Now, once this HCl in the solution is completely neutralized by sodium hydroxide, when no longer HCl will be present in a solution, acetic acid will undergo dissociation. So you know very well, acetic acid will undergo dissociation in incremental ratio or incremental manner. So an OH minus from the base reacts with the H plus from the acetic acid very slowly and partially. So you'll get the another straight line. You can see this second straight line, which is slowly the specific conductance value increases very slowly. That is, the incremental increase in the specific conductance will be observed when HCl will be completely neutralized by sodium hydroxide. Now, after the incremental increase, there is a continuous increase in the specific conductance. Significant increase in the specific conductance. This is due to the when both the acids, strong and weak acids, are completely neutralized by sodium hydroxide. Further excess of sodium hydroxide you are going to add from the burette, and that sodium hydroxide will be containing OH minus highly mobile, and which will add a significant contribution to the specific conductance. So the specific conductance value continuously increases and you get a third straight line. So first straight line corresponds to the decrease of H plus from HCl, and second straight line corresponds to a decrease of H plus from acetic acid, and third straight line corresponds to the excess of OH minus from sodium hydroxide. So intersection of these three straight line will give you volume V1 and V2. The first one will give you volume of V1, and second one will give you volume of V2. Now the advantages, when you look into the advantages, mixture of acids can be titrated, various mixtures of acids, strong and weak, any mixtures of acids can be titrated to obtain the equivalence points. The method is accurate in dilute as well as more concentrated solution. So the accurate method of normality and the amount in dilute solutions as well as in the concentrated solutions. It can also be employed for the colored solutions. And mixtures of acids can be titrated more accurately, and it can be employed for weak electrolytes. So these are some of the advantages of the conductometric titrations.